Have you ever wondered about the square root of I? Is it even possible? Or what about a number like 5 minus 2i? What would its cubed roots be? In this session, we're going to explore such concepts. We're going to look at the roots of complex numbers. It all stems from de Moivre's theorem, and the result is the following theorem. The nth roots of a complex number, z not equal to 0, which has polar form, z is r times the cosine of theta plus I times the sine of theta, then for each natural number n, there are n distinct roots. We denote them by w sub 0, w sub 1, w sub 2, etc., up to w sub n minus 1. And they are given by the formula w sub k is the nth root of r times the cosine of theta divided by n plus 2k pi over n plus I times the sine of theta divided by n plus 2k pi over n, where k goes from 0 to 1 to 2 up to n minus 1. Let me summarize that. So we are finding the nth roots of a complex number z in polar form when we first say the modulus of each root is given by the nth root of r, or r to the 1 over n power. The argument of the first root corresponds to theta divided by n. And number 3, we repeatedly add 2 pi over n to get the argument of each successive root. For example, find the 3 cube roots of z is 2 plus 2i. We start by writing z in polar form, and we have to find the modulus of z is the square root of a square plus b square. We have the modulus of z is the square root of 2 square plus 2 square. And simplifying that, we get the modulus of z is the square root of 4 plus 4, or the modulus of z is the square root of 8, and that can simplify as 2 square root of 2. And then we want to find the argument. Theta is in the argument of z. Then that tells us that tangent of theta is equal to the imaginary part divided by the real part. The tangent of theta is 2 over 2. Tangent of theta is equal to 1. And where is the tangent equal to 1? That corresponds to theta is 45 degrees, or pi over 4 radians. Polar form, z is written as 2 square root of 2 times the cosine of pi over 4 plus I times the sine of pi over 4. Now in finding the cube roots of that number z, denoted by w sub 0, w sub 1, and w sub 2 are the cube roots. The modulus of each root is given by the cubed root of r, and that corresponds to saying the cubed root of 2 times the square root of 2. And we can use properties of exponents here to simplify that further. 2 to the 1, and the square root of 2 is 2 to the 1/2, and this is all to the 1/3 power. And 2 to the 1 times 2 to the 1/2 is 2 to the 3/2, and this is all raised to the 1/3 power. And when you simplify, you end up with 2 to the 1/2, or the square root of 2. The modulus of each of those cubed roots is the square root of 2. Now the argument of the first cube root is theta divided by n. For this example, we're taking pi over 4 divided by 3, and that can simplify as pi over 12. And if we work in degrees instead, 45 degrees divided by 3 gives us 15 degrees, which is pi over 12 radians. The next step, add 2 pi over n to the first argument to get the second. The argument of w sub 1 is pi over 12 plus 2 pi over 3. And you can simplify that as 9 pi over 12, which reduces to 3 pi over 4. In terms of degrees, 2 pi is 360 degrees, and 360 divided by 3 is 120. So basically, we add 120 degrees to get argument of next root. The argument of w sub 2 is pi over 12 plus 4 pi over 3. Or if I start at 3 pi fourths, I add another 2 pi thirds to it, and I can get that same value. Pi over 12 plus 4 pi thirds, finding a common denominator, would produce 17 pi over 12. In terms of our degrees, we start at 15 degrees, and to get the next root, add 120, and 15 plus 120 would produce 135 degrees, and then add another 120, and 120 plus 135 is 255 degrees. So we would have w sub 0 is the square root of 2 times the cosine of 45 degrees, or pi over 4 radians, plus I times the sine of pi over 4. W sub 1 is the square root of 2 times the cosine of 3 pi over 4, plus I times the sine of 3 pi over 4. And finally, w sub 2 is the square root of 2 times the cosine of 17 pi over 12, plus I times the sine of 17 pi over 12.